Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'll be talking about ranking in entity relationship graphs with two issues, learning and performance for doing database queries. So I'll follow through with my motivation, although by now it's sort of preaching to the choir. Suppose a journal editor J, might be me, wants to find a reviewer R from a company for a submitted paper P. So how do you go about it if you had your personal database represented as this entity relationship graph? Well, the submitted paper P should have words which overlap with papers P prime written by the candidate R. And even if such a person R exists, he or she is likely to reply to my request only if there's some prior interaction in my data graph between J and R. So there are all kinds of links. Papers have words. Words appear in other papers. Papers cite papers. People work for companies. So in some sense, I'm trying to anchor these red nodes, the paper, company, and myself, and looking for the gold nodes, candidates R. So observe two things. There are nodes and links of various types. And unlike in standard PageRank, it's very difficult a priori to design magic ranking functions which put together the relative importance of different edge types in a coherent ranking in a scoring system. And the second is that the graph is not all available to you offline. The graph materializes only after asking the query. So this really means that personalized page ranking of different edge conductances is really important at query time, and you cannot really push off page ranking as an offline activity. Okay. So I try to use an example close to academia, but type graphs are really ubiquitous, and we have seen many examples of that through today. There's XML and RDBMS turned into graphs where there are lots of different edge types. Even web search should really be using, and they do use diversified link types, same or different domain, subdirectory links, links from blogs, which are more suspect than static links. Entities mentioned on web pages, like Kevin was talking about, web pages pertaining to topics, web pages tagged with a particular tagging system, collaborative search, person likes movies of genre, drama, and so on. And it's well known from the machine learning literature that a graphical representation adds great power to structured learning tasks. And it's very natural also for ranking, but it's surprisingly less explored compared to labeling tasks in machine learning. So that's roughly the stage. And the work I did, partly supported by Microsoft, had two parts. One is learning to rank entities in such graphs. In particular, how do we learn from relevance feedback the respective conductances of different edge types or edges? And the second is HubRank, which is the algorithmic or database aspects of building good indices and reducing preprocessing time as well as query time using those indices for doing the sort of conductance queries on graphs. So we had a bunch of papers through last year through this year with other papers in the pipeline. We have papers and slides and posters at the following URL. And we have NetRank and HubRank code open source and available for any of you who'd like to play with it. And those are the students. They're all graduated, so I'm absolutely free now. So, OK, so here's standard PageRank. Quick background, just to make the talk self-complete. A node is an entity and edge relationship. Person wrote paper is an edge. Person works in company is an edge. Every edge has an edge conductance, CU goes to V, written in the opposite way, CVU, which is the conditional probability of walking over to V from the node U. That is if you walk, which happens with probability alpha. And with probability 1 minus alpha, you teleport or jump. In case you jump, you go to the node U with the probability R of U. So R is a multinomial probability vector. So it's well known that the overall PageRank equation is this kind of recurrence. P sub R equals alpha C P sub R plus 1 minus alpha times R. And you want to solve this for P. And I subscript P with R to represent the fact that R is the query and PR is the result. By adding a dummy node, you can turn this equation into a more homogeneous form and make P a circulation. And we kind of freely move between C and C hat and P hat throughout the talk when there's no confusion. So that's PageRank in one slide. But observe that in standard PageRank, C is supplied to you, and your job is to find P. So C and R are given, and you have to find P sub R. In most of our work here, we have the inverse problem in some sense. You're given the graph. You're probably given the query induces a teleport vector R, and you're also given certain partial order preferences between the elements of P sub R. And now you have to find C and PR simultaneously. So it's really an inverse problem. I'm giving you properties of the eigenvector, find the whole eigenvector for me, as well as the matrix which leads to that eigenvector. Okay. So that's in general ill-specified, and you have to regularize the problem in various ways. So we'll discuss two aspects of our two formulations of doing this. In NetRank 1, we do a totally local learning of the conductances on different edges. And we produce a formulation based on network flow, and we have shown certain generalization properties and experimentally established scaling and other practical learning rates and so on. And then in NetRank 2, we actually look at C as defined in terms of global edge types, which is what I started off with in my motivation slide. So before we get to PageRank, NetRank 1, let's discuss PageRank in a slightly different light, originally introduced by John Tomlin in IBM. To define the standard PageRank, we set the teleport vector to the uniform probability 1 over V, and then we set all the conductance entries to be uniform. So from a particular node, the random surfer walks out to all the out neighbors with equal probability. And then let the resulting conductance matrix be Q and the corresponding PageRank vector be pi. We define this flow quantity QUV as the joint probability of being in node U and then walking over to node V. Okay, so it's a product of pi U times Q, U goes to V. And now, instead of Q, we're interested in finding a different flow P, UV, so that P satisfies these preference pairs. Okay? So if I say that I like U less than V, what I mean is that the node score of U should be less than the node score of V, where the node score is defined as the total inflow into node V. So PV is the sum of all U's entering into V, PUV. So that's how I set up PageRank as a flow. And we want to find a P which stays as close to Q as possible. That sounds like a reasonable thing to do, but it's not offhand clear why that's a good idea. It turns out that keeping P close to Q is very similar to normalizing or regularizing the scoring function with respect to the Laplacian of the graph. But we'll skip that detail for now. So this is what the optimization looks like. It sort of looks complicated, but it's actually not. So I want P to be close to Q, and we do that because they're both multinomial distributions through a simple KL divergence. So I want to keep P close to U while reducing violations, and those are measured by the slacks marked as these yellow boxes, and that's the usual SVM-like nuisance parameter. I want the flows to add up to 1 because the number of random surfers has to be conserved. I want the number of surfers entering a node to be equal to the number of surfers leaving the node. I also want to satisfy the teleport probability constraint. So it's like there's a synthetic dummy node which defines how often I teleport, and everyone else defines when I walk, and the ratio should be in the ratio of alpha is to 1 minus alpha. And finally, I want the net inflow into U to be less than the net inflow into V assisted by the slack variable S. Okay? So observe that for the moment there's no margin, and we can do margin, but it gets a little more complicated. So that's sort of the optimization, and this has a lot of nice properties. It's sort of a Maxent-like framework, except it has some linear inequalities. So you can dualize this and do all kinds of nice tricks to speed up, do variable inclusion and things like that. So that's in our KDD paper last year. So at that time, it seemed like a nice idea to regularize P using the baseline flow Q, but it wasn't clear if it was doing anything good. So this year we have this paper where we show a pack-like result. We basically show that with probability 1 minus delta, if you're drawing samples of preferences from V cross V according to some unknown distribution, the expected loss on a test performance pair differs from the empirical average loss over training pairs by some quantity which goes down with increasing preference size, which is the kind of result you want to show for convergence, right? We also have bounds with conventional additive margin. So here we don't have a margin, which makes this bound, this particular bound itself nice looking but somewhat weak. But you can strengthen that. And there are very nice connections between what happens if my objective here becomes really small and what P means in terms of smoothness with respect to graph Laplacians. So that's our ICML paper this year. But how does it work in practice? The other nice part about this formulation is that unlike the competition, which uses Laplacian smoothness, we don't really need to diagonalize a giant matrix. The Laplacian sort of doesn't emerge explicitly. We don't need to find a pseudo-inverse. We don't need to diagonalize it. We work straight on the primal system. So it works pretty well in practice also. With the additive margin, we beat the error rate of Laplacians by some visible margin. And also, our algorithm scales linearly in the size of the graph as well as the size of the preference set. Sort of like simple implementations of PageRank, we need to hold V in RAM, but the edge list and the preference list can be scanned from disk. So it's a very scalable algorithm. So the second formulation that I want to talk about is where we don't do local learning of the conductances. We actually have global constraints between the edges on the graph given by edge types. So all edges of the form person wrote paper should have related conductances in this graph. So how do I define that? Let's say there are T edge types, and every edge UV has a pre-designated type TUV. And the weight of that edge is given by some beta of the type. Okay, so beta is my parameter vector. Okay. And given these weights, assuming there are no dead-end nodes, the conductance going from node I to node J is proportional to the weight of Tij. Right? So divided through by all the other neighbors of I, multiplied by alpha to account for not teleporting. Otherwise, it's a teleport to D, and then you teleport back from D into some other node J. Right? So note that C is a function of beta, and so sometimes we write it as C of beta. And also note that scaling beta does not change C. So there's some scale invariance of betas. So therefore, we can write down our goal as finding a beta vector which is all element-wise more than once, such that P solves P equals C of beta times P, like standard PageRank, right? While simultaneously ensuring these linear inequalities between components of P, right? So that's a particularly nasty form, right? If you try to write it down in usual ways, you'll end up with like quadratic constraints thanks to both P and C being unknown. Okay. So to avoid that, we have a bunch of tricks in our PKDD paper last year. So we also want beta to remain parsimonious. The standard baseline cases, all beta are the same. So we measure the divergence of betas from 1, say a quadratic type regularizer. And then we measure some loss function between a finite expansion of power iterations in PageRank. Okay. Unfortunately, this is not a convex optimization, but the surface is sort of benign in practice. Yeah?
The dimensionality beta is the number of types.
Number of types of edges.
Roughly what order of magnitude are you thinking? Like
20, 100 maximum, yeah. So this is
not a very high dimensional optimization.
No. Yeah. So that's why, in spite of it not being convex, it's not that bad in practice. So some local grid search is required for this. So I'll give a demo of this online if things go fine. So our learning rate is very high thanks to it not being a very high dimensional problem. So by the time you give it a couple of hundred pairs of preferences, test error comes down to pretty much 0. The second thing to observe, which you also see live, is that if I hide betas from the algorithm and I want the algorithm to discover the betas back, that goes pretty well. Of course, there are large swaths of beta surfaces which gives the same ranking. So it's not like you can identify a specific beta vector from the ranking alone. That's okay. The other thing we did is we took pair preferences from people and we randomly flipped some fraction of that just to see what happens if we corrupt the training data. Because in real life search engines, people do not have consistent opinion about whether X is better than Y or vice versa. And as you can see here, as I increase the fraction of noise, of course, my error rate goes up slowly. It's not that bad. By the time I've corrupted 12% of the training data, my test error goes up by only about 5%. Okay. But the other interesting thing to note is that the algorithm steadily decreases its investment in the model. So that's a nice debugging check on the algorithm to see that right things are happening. So let's see if I can show you how the parameter estimation works. So there are two graphs here. One is a plot of true beta to estimated beta. So initially all the estimated betas are the same, and then they start deviating, and my error rate is also starting to go down. The first, yeah. So ideally you would like a y equal to x graph here, but because of the equivalences in the ranking space, that doesn't always happen. In this case, it will not finish up there. But as you can see, the training error is already going down within 3 or 4 iterations. And now you can see this guy dropping below, and those guys are already pretty small. And as that happens, the training error is pretty much down to 0. Okay. So basically, it's a very simple sort of grid search plus gradient descent algorithm, which seems to be very good at detecting at least a rough ballpark of the beta orderings that were used to generate synthetic data with some corruption. Okay. So that's that. Bring on the giant hammer here. There we go. Okay. So to continue, the second half of our work was, okay, so suppose a machine learning algorithm has fitted the parameters of your conductance system. How am I going to evaluate queries in real time without doing static page ranking offline? As I argued, you cannot push off all the page ranking work to offline operations. You have to do certain things at query time. So, and the goals are small index size, small preprocessing time, fast query processing, and high ranking accuracy with respect to the reference page rank computed over the whole graph at query time. So just to get back to some of those equations, if we rewrite P of R in this form, you see that it's basically some matrix you never want to evaluate explicitly times R. So it's linear in R. And query time power iterations are too slow, as we shall see, for even graphs of very small size, which fits into a laptop. And there's this paper from UC San Diego several years back called Object Rank, which proposed that you pre-compute what are called personalized page rank vectors for all the words. So think of setting up an impulse vector on every word taken as a node, which then connects to all the nodes where that word appears, right? And so delta W is a vector which is 1 only at the node W and 0 elsewhere. You compute the personalized page rank for every word, and then because this operation is linear, you put together those things into a combined score and pick the top k guys out of that, which can be done very fast. The problem is that typically for any corpus, the vocabulary sort of scales weakly or almost linearly with number of nodes. And this computation becomes really, really impractical. So even with our toy data set, which I have on the laptop, with 75,000 nodes and about 500,000 words, the estimate is that my laptop would take 22,000 CPU hours to calculate all those PPVs. So we really can't do that in practice. So the contribution of the HubRank project is to cleverly select a hub subset. So there's a set called H, which is a subset of nodes in the graph, which includes word nodes as well as entity nodes. And then and that's driven by the query logs in a very strong way. So we pick nodes which block PageRank expansions from the query points, from the teleport points. And I don't really have time to explain the algorithms in detail. And then you compute the PPVs for only the hub nodes. Okay? And that involves, the way we pick the hub nodes depends a lot on our query processor, a detailed performance model for the query processor. And that decides what the hub set is going to be. And then there is yet other tricks to calculate the hub set PPVs much faster than the obvious way. And that's stored in a PPV index. And at query time, we can reconstruct PR from only the PPVs calculated for the hubs. And there are two ways of doing it. And the first is an active subgraph PPV reconstruction that's in a web conference paper this year. And the other is an asynchronous prestige push algorithm, which is patterned after a paper by Frank, which is in preparation. And the bottom line is that we get a very graceful trade-off between the amount of offline preprocessing that we invest, the index space that these PPVs take, and the query time when you ask a query. So I'll just present some of the numbers here. So this is like first generation HubRank, that's second generation HubRank. And to give you some reference here, the Lucene text index over this particular corpus takes about 55 megabytes, which is right there. In the first generation, we took about 50 megabytes of index space. And we took about, between 12 to 200 milliseconds to answer the query, about 200 milliseconds in the first generation, which is still orders of magnitude faster than the whole graph page rank, which would take about 10 seconds. In the second generation, we have cut down the size of the index by about a factor of 10, and we have simultaneously cut down the query time also by a factor of 10. So you can, I'll be happy to give you preprints of our new work, which lets us do that. So as you can see, our index sizes are now much smaller than what even a basic Lucene index would take. Our preprocessing times are 2 to 10 hours, which I won't run now, but I'll run the queries. And then our query time is order of milliseconds as compared to several seconds. And this scales up arbitrarily with the size of the graph. If you give me a larger graph, whole graph page rank will take indefinitely larger times, whereas it seems like as long as you can hold the size of the hub set to the node set roughly fixed, we are okay with query times. Our query times do not scale with the size of the graph. Okay. And I don't have time to talk about that, but this holding h over v to be roughly fixed is not so dangerous as you might think. We can actually compute the PPV index in time, which gets sublinear with increasing size of the hub set. Okay. Because you can reuse earlier hub calculations in doing later hub calculations. Okay. So here are some examples. So suppose you take network security. I'll also use this opportunity to show you that good things happen in terms of what the ranking function does on a sightseer database turned into a graph. So here's network security. And the browser, we're running PageRank here over the whole graph of 75,000 nodes. And this is a fairly simple Java implementation, so it's not lightning fast. But we're using the exact same access method for both the routines, so the ratio should be fairly okay. So we're taking 8.3 seconds in this case. And you can see the usual names at the top. So here are authors in the natural ranking order, but there's also papers mixed into the same thing. And if you had organization nodes, which Sightseer does not, I'm sure the best organizations will also come to the top. So in particular, we have a more detailed query language we're developing, similar to Kevin's query language, where you can say, I want certain target things to be ranked with respect to network security. Don't just rank all nodes, rank people with respect to network security. So I can do that. So that was the timing, and now let's go back here and try hub rank. That's the response time. So whereas that took 8,000 milliseconds, this took 63 milliseconds. Okay. And the results are absolutely the same. So results are almost always identical. But that's not provable, but our epsilon differences in rank correlation are very, very small. If you come to something like this, you'll see that the whole graph page rank is very insensitive to what query you're asking, because it's basically doing similar eigen computations over the whole thing, 8,000 milliseconds. How did this come in? Because of PCP here. It's a very popular old paper. Whereas, okay, so as you scroll down, you see the usual suspects of PCP, Mario Segedi and Carsten Lund and so on. Whereas if you ask about using hub rank, that's a response time. And this is for a tiny 74,000 node graph. If you give me a 1,000,000 node graph, our response time is sort of the same. Scales very mildly. Whereas PageRank pretty much scales linearly. Okay. So that's sort of the demo of that system. And there's one other thing, which is typically when people calculate PageRank, they depend on L1 tolerance to stop the calculation. And it's known that that's no guarantee of rank stability. Ronnie Lempel and Shlomo Moran had a paper last year, or 2 years back. We have a new algorithm which gives you guaranteed top K ranking, but actually it's top underline K, overline K ranking. So if you ask me to get 20 things, I might be returning you anything between 20 and 40 things. But very often I'm able to terminate my algorithm even earlier and faster by about a factor of 3 consistently, because I can bail out earlier by keeping bounds on the maximum and minimum possible PageRank values of all the nodes. So that's another development. So now coming to plans with Microsoft Search Assets. So when we started out, we wanted to do extraction, scoring, and learning to rank, and finally the database issues of scoring rapidly at query time. So it turned out that we were working our way backwards. So we first developed the graph paradigm of ranking, learning scoring functions, and work node cognizant indexing and query optimization. So now we're getting into how the query logs and the live search can help us extract structure, types, and attribute information. So if you look at existing approaches led by Noitol and other projects, which try to use live search engines in doing bootstrapping, using patterns and lists, they are pretty much still stuck at counting hits. They generate smart queries, and then they see how many pages Google thinks has cities such as London, and then use that as sort of a very noisy feature to decide what they're going to do. And there are other systems which do very similar things, like Andrea's system. So information carnivores are reduced to this fairly low-tech state of affairs because anything else involves too much work. You have to actually fetch the page, and you have to process the page in your own way, perhaps differently and in a more sophisticated way than what the search engine itself was doing. The main reason why I haven't been able to use the API so far in a way that's plugged into a meaningful machine learning framework is that there's no guarantee about which particular hits I'm getting. The count may be okay if you're lucky, and if the search engine is careful about how it generates the counts, but we definitely need flexibility in defining what sample I get in the top 500. I want to sample uniformly, or maybe I want to do a stratified sampling. There is technology for that. So Pingley and Ken Church had this paper last year about sampling from the results of queries. We definitely want to have that before we start plugging in search results into a bigger system with guarantees of any form. And also, Andre Broder and others had this paper in the last year's web conference on doing that. The other problem is, okay, so once you get back the page, as Kevin was saying, all you know is that there is a correlation, right? That's a very zeroth order information. To take it beyond that point, we need a more meaningful representation of features on that page. Okay? So what we need is really a catalog of features that maybe the people who are sharing this search service can define, and there has to be some sort of a consortium of people interested or stakeholders in the search system in Microsoft who say, okay, so we have these 200 features defined on the page, which our scanner in the crawler can determine very quickly, and we'll index on that. Like starts with capital and then doesn't have capital letters, or has 4 digits, or it looks like a date, right? Surface patterns to start with, but maybe connections to ontologies or connections to taxonomies like WordNet, right? So here's a token which connects to mammals in WordNet. That's a flag. Now, of course, you could define like 100,000 of those, and that would be too expensive for Microsoft to index. But there are interesting optimization questions here. Suppose I want to tag mammals as well as insects. Can I say living thing? And then maybe you'll have to do a little extra work when you get back the page to sharpen what you want to do with it. Okay? So we need that, and we also need aggregations on those features. I want to be able to ask, okay, of all pages that mentioned tiger, how many of the pages mentioned a place in it? Okay? Because eventually I want to use this to derive conditional probabilities. And how do I define probabilities unless I know that things are sampled properly from the entire space of documents that are available? Okay. Or maybe you sample by page rank, but I need to know what. So if it's a strange mix of anchor text match and page rank and something else, right? I cannot generate meaningful probabilities or feature spaces from that to use in other learning algorithms. Okay. And then you need more schema capability on the query than standard text box, because the Google API or the MSN API, they are nice ways to get around doing the page scraping to get back the answers. But what I need to do is to inject queries like find me an instance of a city near a mention of tiger. Okay. So something like the bindings engine or something like Kevin's query language. I had one paper in last year's web conference. Maybe we can put some of those together and define a schema-light query language which can be supported by this API before we can plug it into other interesting next generation know-it-alls, systems like that.